Welcome back. Let's move on. Just going to make sure audio is working here, and yes. And here we go. Let's look at some mechanisms. I copied the top line of our review that we just did in our previous segment, and we're going to do the acid catalyzed dehydration of ethanol. And to do so, we first must protonate our alcohol, which means we require sulfuric acid, and we need to see this bond. Usually on tests, I try to make sure that bond's already visible. And we need a lone pair on our oxygen, and it attacks the strong acid's proton, and we generate an oxonium ion thusly. Now, when we're talking about dehydration of alcohols in section 10.5, there's two main options after this. Let's copy down our conjugate base. The two main options are an E1 mechanism, which would have to go by way of a carbocation. I do not want to see you draw primary carbocations, and that's what this carbon is. So we must entertain option 2, which is called E2. It's the only option here where the alpha carbon loses the leaving group. In this case, it's water. And the beta carbon loses an H. And the mechanism goes like this. Making pi, that's what elimination is always about. I don't like that arrow. Start over. We want nice arrows on our mechanisms. Go slow and don't press hard. That's what I'm learning about my new system here. Okay. And we got a little bit of a little mess there I got rid of. Okay. We made ethylene here. We're going to brominate ethylene using step 1 here. We're going to make a vicinal dibromide as discussed in section 6.1D. And we're going to react it with BrBr in step 1. There's a lone pair. There's 3 lone pairs on each bromine, but only 1 necessary for the mechanism. Alkene attacks the bromine, and bromide leaves. If I had only those 2 arrows, I would make what I told you I don't want to see, which is a primary carbocation. Don't do that. As soon as the carbon starts feeling positive, this bromine comes and gives it a pair of electrons. Usually we come back to the more substituted carbon. In an example with a symmetrical alkene, it matters not which carbon you come back to. So we have this, a cyclic bromonium ion. And we also have bromide anion. Bromide anion is a nucleophile which will attack the least hindered carbon. Oh, that's not the case here. It would attack the better carbocation. This is a cation intermediate, isn't it? It's not about attacking the least hindered carbon. Once again, it matters not. Both sides have the same substitution. It's equal stability for carbocations. Backside attack. Leaving group does its best to leave. It can't leave entirely because it's tethered on both sides. And what do we have here? We have this bond to bromine, which did not go anywhere. New bond to bromine. And that's the end of step 1. Vicinal dibromide right here. And what's going to happen here in this? This is a tert butyl group. It's not the best drawn tert butyl group, but it's attached to an O-, making it a strong base. There's H's on each side. So if I call that H there, the one that's going to be removed, then I'm making that the beta carbon, and this the alpha carbon. Try to draw my tert butyl a little better this time. Nice. Tert butoxide is what that's called. Grab the H. Sigma becomes pi. Bromide leaves. This is classic E2. Nice way to make new pi bonds. So now we have our pi. We still have an old bromide from before, which we didn't get rid of. And we have an H over here. If I call that the beta, well, I don't have any choice this time. Alpha is the one with a bromide, and beta is the one with the H that needs to be removed with our second mole of tert butoxide to make acetylene. Let's see how well this works. Nice. And tert butoxide number 2 right here. Grabbing the H here. Oh, off screen. Doesn't like it. Grabbing the H. Sigma becomes pi. Bromide leaves. Voila. You have acetylene. And the last step is a simple one, isn't it? Acetylene becoming acetylide. We're going to have to show the H here. I'm going to cross off the spectator here, put a lone pair and an anion. Crossing off spectators is not the end of that story. You cross off the spectator, replace it with the charge it was balancing. Please don't forget that. That's throwing away a half point. Don't throw away points. All right, H lone pair grabs H. Sigma becomes lone pair. And we have acetylide. All right, let's save this file. Let's go grab another segment from the original. I think my easiest way, we only have 3 pages, so we can go back. And you notice I fixed up the original page, got rid of most of the answers. And we're here. Why don't we grab like this stuff here? We'll see. No, we're gonna need our snipping tool. Where did I put Snippy? He's lurking. There he is. And I don't want things to get too cluttered. I think we can get all that in there. And move on to our page 4, which doesn't exist yet. Here it is. And we'll get rid of stuff we don't need. Dangerous big eraser here. Careful. Okay. Put it up here. Acetylide. Here we go. Acetylide has lone pair on carbon. Lone pair on carbon can attack, backside attack on a carbon with a leaving. Well, that's a pretty lazy arrow. Coming right to the carbon. Bromide leaving, giving us something I cut off. An ethyl group on there now. And I forgot to grab the chemicals. I should have got this from the answer key, huh? Well, on the top reaction, we had HB-Sia2 in step 1. In step 2, OH negative and hydrogen peroxide. Okay. And the bottom one, let's do one at a time. This attacks what atom again? Does it attack a more positive boron or a more negative hydrogen? Remember, we're talking about electrons being the attackers. Electrons do not attack things that have a minus charge or even a partial minus charge. Attacking the less positive boron, the bond between hydrogen and boron breaks. Hydrogen keeps the electrons and makes a sigma bond to the more substituted carbon. Both of these arrows happening at the same time means syn addition. We'll put the mechanism down the right side here. So right now, got rid of one of the pi's. We got an H on the more substituted carbon on the same side of the alkyne as the B. And we can go R2 as long as we acknowledge sec isoamyl is R. And that's the end of step 1. Step 2 is where all the money is. Money equals points. Step 2 gets started with an acid-base reaction, and step 6 will also be an acid-base reaction. Acid-base between hydroxide base, hydrogen peroxide acid, generating a peroxide anion. Peroxide anion. Remember, the first time you generate an O- in this mechanism, it does the same thing the second time you generate an O- in this mechanism. It attacks the more positive boron. Boron doesn't do SN2 reactions. Burn that into your brain. Boron's a little machine that loves alternating between 3 bonds, which we see here, and 4 bonds, which we're about to see. We don't need to show that H anymore. And we have a new bond here. And boron with 4 bonds, it's a group 3 element on the periodic table. Boron has an anionic formal charge. Now here's where our alkene goes from having a less electronegative boron to having a more electronegative oxygen. And the reason for this happening is to get rid of an OO bond, which suffers from lone pair repulsions, and get rid of our formal charge on boron. It's a stability twofer. We get now R2B is attached to that green O up there, which is now attached to the carbon that's on the end. And boron's got 3 bonds again. And don't forget the other product here, because that's your memory trigger. This is the second O minus you made. You do the first thing, the same thing you did with the first O minus that you made. Here you attack the boron, because the boron's very positive. Don't do an SN2. All right. Moving down. R2B bonded to O, bonded to a C, double C with an ethyl. And now we have an OH down here. Boron's got a minus charge because it's back to 4 bonds. Okay. So here's where we have to interchange this bond from boron to this oxygen with this bond from boron to oxygen. We're going to lose the old bond from boron to oxygen because we put a new bond from boron to oxygen right here. It's a trade. In the text, to help us remember the steps in this mechanism, we usually number them. You do not have to number them on tests, but just for old time's sake, the first one was the acid base. The second one was attack. The third one was a rearrangement. The fourth bond was another attack. Fifth step, was losing the other oxygen off boron. And that means we're setting up for an acid base in step 6. We now have R2 bonded to B, bonded to O, which has a bond to H. We also have O minus. That's the conjugate base of a type of alcohol. We didn't do the pKa's of boric acid derivatives, but they're much less than 17 because they can resonate the O minus with the B. You don't need to learn any number there. Just remember, acid base happens here in step 6. And here we have step 6. Don't want to go too deep on the page. Makes your notes too small. Move it to the right a little. Remember your goal. We don't even know our goal. There it is. It's butanol up there. And your goal is to get here. Okay. We're clearly not there, are we? You're going to have an O bonded to an H. Alkene. Right there. And boron's done for the day, but if you're curious what it became, it's a borate ion. Sometimes my thing does not like drawing where I put it. That's fine. That's just a badly drawn 2, people. Maybe it likes it better if I do it here. My pen's off. It's a worse drawn 2. Okay, how do we get from there to butanal? Step 7 is the step you didn't see in chapter 6 because you didn't have an alkene. It's called tautomerization. Do you remember what happens during a tautomerization? We move two things. We move a hydrogen atom. Clearly, when we're making butanal, there's no hydrogen on oxygen. Let's just copy butanal here. So you have to move an H. It goes from here to the next carbon over, which is now a CH2. Previously, it was a C with one H. So something's got to take that H, and its conjugate partner must provide the H for this carbon. The things available in this reaction are hydroxide and its conjugate base. Hydroxide and its conjugate base, which I'll put, I don't know, I'll sneak it in here. Water. Hydroxide grabs the H. Sigma becomes pi. Pi breaks and protonates from the conjugate acid. And that brings to a close our longest mechanism of last semester. We're not going to get too many longer this semester either, so don't be thinking 242, higher course, bigger mechanisms. It's about as big as it gets. The mercury one is slightly smaller, but let's take a break so I can get organized for the mercury one and call this segment 2. Sound like a fair deal? Following our protocol, stopping the share, and I'll see you in 5 minutes. This one will be 5.